Today we're going to talk about a technique called implicit differentiation. Well, implicit differentiation is a useful technique when, for whatever reason, your original equation cannot be solved for y. So, for example, if you had the circle of radius 3, again, circle of radius 3, it has the equation x squared plus y squared equals 3 squared. And if you took that and tried to solve for y, you wouldn't really be able to without having to consider the function in pieces. So for example, x squared plus y squared equals 9. If you tried to solve this for y, you'd start off with y squared equals 9 minus x squared. And then if you tried to solve for y, you'd be talking about plus or minus the square root of 9 minus x squared. Well, in terms of taking a derivative, the biggest problem is that you have two different parts. You have the positive part and the negative part, so you'd have to consider two different cases. Plus, you've got a square root to take the derivative of as well. So in this situation, it would be nice if there's some way we could take the derivative and leave the function in this form rather than trying to write it in that form. And there is a way to do that we're going to learn today. Now, alternatively, another situation where you might need it, let's say, for example, you had the function x equals y squared. Well, you know, y equals x squared looks like the parabola centered at 0. But x equals y squared is actually parabola centered this way. Now, if you tried to solve this thing for y, you would get y equals plus or minus the square root of x. Well, the plus part, plus square root of x, would be this portion right here. And the minus square root of x part is the square root of x function flipped down, which would actually be the bottom part of the function. So you would have to, if you're going to do a derivative, you'd have to do it in pieces, which is undesirable. So, method of implicit differentiation would be useful. So, think first about this. Suppose you had y equals 3x plus 2. So suppose you had y equals 3x plus 2. And you needed to take the derivative of y to the power 5. Well, the derivative of y to the power 5, well, remember that y is 3x plus 2. So that would be 3x plus 2 to the power of 5. Now, to take the derivative of that requires a chain rule. This would be 5 times the inside function left alone, all to the power 4. And remember, with chain rule, you have to multiply by the derivative of the inside function. So this is something to the power of 5. The derivative of something to the power 4 times the derivative of that inside something. So recall, in that situation, you had d dx of 3x plus 2 to the power 5. That was 5 times 3x plus 2 to the power of 4, all times the derivative of the inside part, which is 3. Well, if you were finding d dx of y to the power of 5, and let's suppose that you didn't know what y was, if nobody had told you it was actually 3x plus 2, so you couldn't see that stuff written in orange. all you could do is derivative with respect to x of y to the power 5 is 5y to the power 4. Now you know you need a derivative of the inside part because y could be anything. Now if it had been x to the power 5, you'd be done. It would be 5x to the 4th. But since it's y, you could potentially have a derivative of the inside part. So you need to write this as 5y to the 4th times y prime. And this is the basic idea of implicit differentiation. So if you're ready, we can go ahead and take a look at an example. So take a look at this example. We're trying to find the derivative for the equation of the unit circle at a particular point. Well, recall on the unit circle, that point that they're talking about, 1/2 comma square root of 3 over 2. Remember, the unit circle is a circle of radius 1. The point 1/2 comma square root of 3 over 2 corresponds to an upward rotation from standard position of the angle pi over 3, or 60 degrees. Just to give you a quick reminder, the unit circle, the angle in question corresponding to the point that we're looking at, 1/2 comma square root of 3 over 2, is right here. So what this problem is actually asking us is it's asking us to find the slope of what would be the tangent line if you consider the tangent line to the circle at that particular point. Well, obviously that's going to be a negative slope, but we won't know its exact value until we do the derivative. So recall, slope of the tangent line is the derivative. So what do we need to do here? Well, we need to take a derivative. Now, since our original function is difficult to solve for y, the best thing we can do is use implicit differentiation. And the way you do implicit differentiation is you just take the derivative with respect to x on both sides of the equation. That's the technique. Now remember, you can do a lot of things to an equation as long as you do it to both sides. So here we go. Now when you take the derivative with respect to x, that's of x squared, that's just 2x. Nothing is happening there with a chain rule because the derivative is with respect to x and the function is just x. So d dx of x squared is just our usual 2x. But next, when we take the derivative of y squared, it's not just 2y, because remember, we don't know what y is. It could have a derivative itself. So we got to write that as 2y times y prime. And remember that the derivative of any constant is just 0. So at this point, we've taken the derivative on both sides. Now, since they asked us to find dy dx, we're going to go ahead and do that. Now remember, dy dx is the same thing as y prime. So to finish this up, all we've got to do is solve for y prime. So 2y y prime equals negative 2x, right? And if you divide both sides of the equation by 2y, you get negative 2x over 2y, which is just negative x over y. So that's it. That's the derivative. So we found dy dx. Now, as soon as you're ready, we can go ahead and get the slope of the tangent line. So pause the video if you're still taking notes. Otherwise, we're going to move on to finding the slope of the tangent line. Now recall, we found y prime, or dy dx, to be negative x over y. And we're actually asked to find the slope of the tangent line. Well, remember, the slope of the tangent line is the derivative. We just need to calculate the derivative at that particular point. Well, remember, the first coordinate is x, second coordinate is y. So all we've got to do here is put in a negative. The x is 1/2. The y is square root of 3 over 2. And then just to clean this up, we can multiply by the reciprocal, just dividing fractions here. This gives us 1 over the square root of 3. So the slope of the tangent line, just like we said, is negative, and the exact value is negative 1 over square root of 3. All right, so if you're ready, we'll go on to the next example. Next example, we need to find the derivative of the function y squared equals 4x. So same problem, can't solve for y without making a mess, so y squared equals 4x. The technique for implicit differentiation, take the derivative with respect to x on both sides. Well, the derivative with respect to x of y squared is 2y, and then remember you've got the chain rule part. Derivative with respect to x of 4x is just 4. Since there's no y in that, we don't have to worry about a chain rule. Which means that y prime equals 4 over 2y, which really means that y prime is 2 over y. And that's it. Remember that the derivative of y with respect to x, y prime is just another notation for that. So the answer is 2 over y. So that's the answer for that one. Now what we can do is go on to the next example if you're ready. So cosine of y equals x. Well, you couldn't solve this for y unless you took cosine inverse on both sides. We would like to not have to deal with cosine inverse if possible. So we're going to try to use implicit differentiation here. We know the derivative of cosine, but might not know it for cosine inverse. So cosine of y equals x. Well, we're just going to take the derivative on both sides with respect to x. Well, let's think about what the derivative of cosine is. Well, recall that the derivative of sine is cosine. But if you're taking the derivative of cosine, recall that's the one where you got the minus, so it's negative sine. So taking the derivative of cosine of y is going to be just like this, except we've got the chain rule, so we're going to have times y prime. So this is negative sine of y times y prime. And the derivative of x is just 1. So last step to solve for y prime, divide by negative sine of y on both sides. And that gives you your answer. So final answer is that the derivative of y with respect to x is just negative 1 over sine of y. Okay, so if you're ready, we'll go on to the next example. If not, be sure to pause and take notes and rewatch if needed. All right, so let's say we're working with the function sine of x times y equals x plus y. Obviously, this would be very bad to try to solve for y. But amazingly, we will still be able to take the derivative of it, and we'll do that using implicit differentiation. So what I'm going to do is I'm actually going to give myself a little extra space here, if that's all right. So we've got sine of x times y equals x plus y. We are going to take the derivative with respect to x on both sides. Now, derivative of sine is cosine, right? So we know that here we're going to be dealing with cosine. But the biggest issue is that what we've got inside of the sine function is actually a product of two functions. If one of these was just a constant, we wouldn't be worried, but since it's two functions, we've got to worry about it. So, continuing on, we know the derivative of sine is cosine. But then what happens here is we've actually got to do a product rule. We've got a first function and a second function. So the product rule tells us this is derivative of the first times the second plus first times derivative of the second. So the first function, the derivative is 1. Second function left alone is just y. First function left alone is x. Second function, take a derivative. This is the derivative of y, recall, is y prime. So that's that. Now for the right-hand side, derivative with respect to x of x is just, we know that's just 1. Derivative with respect to x of the function y is y prime. Notice how we don't need any kind of rule over here because you're allowed to take a derivative when you're adding two things. You can take it piece by piece. It's only when there's a product or a quotient that you need to consider a rule. So what is this reduced down to? Well, if you consider distributing and rewriting, what you've got here is just y times cosine of x times y, then plus you've got x y prime cosine of x times y. This is equal to 1 plus y prime. So it's important to understand at this point we've technically taken the derivative. All we need to do is solve for y prime. So if we consider subtracting cosine of xy to the other side and subtracting y prime over here, what we've got is x y prime cosine of x times y. And again, I'm subtracting y prime on both sides, so I end up with a minus y prime here. Now on the other side, I've got 1, and I'm also going to subtract this part since it does not have a y prime in it. So subtract it to the other side. All right, so at this point we're doing well. We just need to factor out a y prime and then divide by what's left over, and we're almost done. So if you factor out a y prime, what you're left with here is x times cosine of xy. And then this is minus 1. So last part, we got to divide both sides of the equation by what's attached to y prime. So y prime is equal to 1 minus y cosine of xy all over x cosine of xy minus 1. And that's your derivative. For that particular problem. Let's try another one. So we're trying to get a derivative here. Be a good idea to use implicit differentiation. So what we're going to do is, we've got cosine of y squared plus x equals e to the power y. So first we're going to take d dx on both sides of the equation. Now the derivative with respect to x of cosine of something, remember derivative of cosine is negative sine. Keep the inside function y squared left alone. Then you've got to multiply by the derivative of y squared. Well, remember the derivative of y squared is 2y, y prime. Now the derivative of x, we don't have to have a y prime part because it's just x. So this part, derivative of x, is just 1. Now derivative of e to the y is going to be, remember, e gets left alone, and then you multiply by the derivative of e. So we can rewrite this as negative 2y, y prime, sine of y squared, minus ey, y prime, and then subtract 1 over to the other side. So basically you've gotten everything with y prime over to one side. Now factor out y prime. You've got negative 2y sine of y squared minus e to the y. And this is all equal to negative 1. Now the very last step, since you've got y prime times something, is just to take that and divide it to the other side. So y prime is actually equal to negative 1 over negative 2y sine of y squared minus e to the y. Now if you wanted to, you could write that as plus e to the y and factor the minus sign out. Then the minus signs would cancel, top and bottom. So you'd really be left with, you could rewrite this to make it look better, 1 over 2y sine of y squared plus e to the y. So that's the derivative of that one. So let's do one final problem, one final example. Calculate d dy for the following function. So we've got 6x cubed plus 7y cubed equals 13xy. Well, just take d dx on both sides like we always do for implicit differentiation. Okay, d dx of 6x cubed. Remember, there's no y there, so there's no problem. This is just our usual 18x squared. Now for the 7y cubed, that's going to be 21y squared, and then times the derivative of the inside part, y prime. But what we've got over on the right, notice we've actually got a product of two functions. We've got 13x and y. So to do the derivative, we've got to do the product rule. So the derivative of the first function is just 13. The first function is 13x, derivative is 13. Second function left alone is just y. First function is 13x. Derivative of the second function, remember, derivative of y is y prime. So what we should do, look at all the y primes on the same side and get all the stuff that doesn't have a y prime on the other side. So we've got 21 y squared y prime. Now I'm going to move the 18x squared over. So this will be a minus 18x squared. Similarly, the 13x y prime, I'm going to move it to this side, so it becomes a minus 13x y prime. Now I can do what I always do, factor out a y prime. 21y squared minus 13x is equal to what's on the right. Final step to solve for y prime, do the division. 13y minus 18x squared divided by 21y squared minus 13x. And that's our answer. That's the derivative. That's our dy dx. Thank you for your attention.